failure to protect critical equipment leads to two serious consequences. If protection is delayed or fails to clear an internal fault, the resulting damage can be catastrophic. Conversely, if protection trips for a fault outside its zone, a healthy system is unnecessarily shut down. Both are costly. Both are avoidable. But only if protection is highly sensitive and 100% selective. Among common protection schemes, differential protection stands out. It is highly sensitive and inherently selective. The working principle of differential protection is simple. It is based on Kirchhoff's current law. The law states that the sum of currents at a node must be zero. In a power system, this principle is applied to a defined zone of protection, created using current transformers, or CTs, placed around the equipment. The relay continuously compares the currents entering and leaving this zone. Under normal load, the incoming and outgoing currents are balanced. The sum of currents in the zone is zero. So there is no differential current, and therefore, no tripping. The same logic applies to an external fault. A large through-fault current flows through the system. It enters the zone and leaves the zone. Since the currents still balance, the sum remains zero. So the relay sees no differential current, and ideally, remains stable. Now, when a fault occurs inside the zone, this balance is disturbed. The sum of currents in the zone is no longer zero. This creates a differential current, which causes the relay to trip immediately. This means, in theory, differential protection is highly sensitive and perfectly selective. It responds to all internal faults and ignores external faults and normal conditions. Because of this, differential protection is widely used for generators, large motors, and transformers, where fast and reliable protection is critical to minimize damage. But in real systems, things are not so simple. Especially during external faults, when currents become asymmetrical and very high. At such high currents, current transformers may not reproduce the primary current accurately. If both CTs behave in exactly the same way, there is still no issue. But in practice, they do not. One CT may saturate more than the other. And this is where the problem begins. Even though the CT primary currents are equal, the secondary currents are not equal. This creates a false differential current. The relay now sees an imbalance and misinterprets an external fault as an internal one, leading to a nuisance trip during an external event. So in differential protection application, one of the challenges is, how do we keep the protection sensitive enough to catch small internal faults, but secure enough to ignore false differential current? There are three approaches to tackle this challenge. First, increase the pickup setting or introduce a time delay to ride through transient CT saturation. But this reduces sensitivity and delays fault clearance, which is not desirable for critical equipment. Second, add resistance in the differential path. This creates a current divider that forces most of the false differential current away from the relay. This method is known as high impedance differential protection. Third, use restraint based on through current. The relay operates only when the differential current is significant compared to the through current. This is called percentage restrained or low impedance differential protection. This approach provides a balance between sensitivity and security. In the next videos, we will explore high impedance and low impedance differential protection in detail. Thanks for watching.